For this, we're going to go through first the motivation, so the background information of what's motivating me to look at the rigidity of intermingled point and sphere configurations. And then from there, we are going to look at the tools that I use in this area, because we're all using different tools depending on what exactly it is we're looking at. So just make sure that we're all on the same page with those. Then we're going to move to the context of Lorentz space, and that's where we'll do the work with objects, the vectors and subspaces that correspond to the objects that we're interested in, spheres and points. We'll come up with a rigidity statement there that translates easily to a rigidity statement in hyperbolic space. And from there, automatically we'll get a statement for configurations of spheres and points in the n-1 sphere. Okay, so to start off with, Beardon and Minda in their paper Conformal Automorphisms of Finitely Connected Regions had two main theorems that they looked at. The first being that if you have two collections of finitely many disjoint circles where you know that the corresponding the inversive distance between each pair of circles is correspondingly equal between the two collections, then you know that there is an inversive transformation taking one collection to the other. And so at this point, I want to say that an inversive transformation I'm considering to be a composition of reflections through circles in the two-sphere. And I'm reserving the term Mobius transformation to mean a composition of an even number of reflections through circles in the two-sphere. This is different than Beardon and Minda use. They call a Mobius transformation what I call an inversive transformation. I'm reserving the Mobius transformation for the orientation preserving transformations. So that's one of their theorems. The other theorem is that given two collections of points in the two-sphere, that if you know that the absolute cross ratio between every four tuple is correspondingly equal, then you know that there's an inversive transformation taking one collection to the other. And in this paper, they ask two questions at the end. They ask whether the conclusion is valid when the circles that you're looking at are allowed to do whatever, meaning intersect, be disjoint, or be tangent. And Crane and Short answer this, saying that yes, as long as you have appropriate conditions met, that you do have rigidity. And the other question they ask is whether or not both theorems generalize to higher dimensions. And again, Crane and Short answer yes. They tackle these questions in their paper Rigidity of Configurations of Balls and Points in the N-sphere. And one thing I want to point out is that in both cases, both papers, the theorems both theorems involve using a maximal amount of conformal information between the collections that you're looking at, which isn't bad. It's just something that I like to look at things. I like to ask the question, how much information can you get away with losing as far as conformal information goes? And then the other thing that they both do is they both consider the theorems for points and theorem for spheres separately. And so a natural question that I asked off of this was, can you consider the rigidity of these configurations of points and spheres together? And so that's what we're tackling here. This is the idea of what I mean by intermingled point and sphere configurations, just collections of circles and points together. And so before we move on, I do just want to point out that the conditions that Crane and Short specify in their paper is that the collections of circles that you're looking at can't all have a point in common. And so the counterexample that they show in their paper is the one that I have drawn out here, which is, you have these two collections of 4 circles. And if you look at each collection, they all have the same inversive distances correspondingly, that C1 and C2, for instance, are tangent, and so are C1 prime and C2 prime. C1 and C3 are orthogonal, and C1 prime and C3 prime are orthogonal. But there's no Mobius transformation taking one to the other, because what's been done is C4 was moved down to get C4 prime, and so there's no Mobius transformation taking keeping three circles constant while moving the other one in this format. So that's a counterexample for why we would want to keep out those collections of circles that contain a common point. So just to give a quick rundown on what inversive distance is, it's just an idea of how two circles interact with one another. And I personally like the formula for inversive distance that writes it out as when they're intersecting. This is my notation for inversive distance. It's cosine theta. And so that's just the theta that you're getting from the intersecting circles there. So it's between -1 and 1 when they're intersecting. And of course, it's 1 or -1 when they're tangent, considering whether the angle is 0 or 180 degrees. And when the circles are disjoint, then it's slightly different, but still similar. It's or similar looking. You're gonna take a circle that's mutually orthogonal to both of the circles and use that as the ideal boundary for a hyperbolic plane, and then measure the hyperbolic distance between the two circles. And the absolute inversive distance is given by the hyperbolic distance used in the hyperbolic cosine there. And so we just say when their interiors are disjoint, that this is positive, and when the interiors are not disjoint, then that's the negative case. And of course, there's an orientation that's being put on each of these circles, and on this side, in this column, this is where the orientations are going in the same direction. And then you could, of course, flip the orientation of one of them, and then that's going to change the sign of what you would have gotten over in this case. So just what inversive distance is. And then the other conformal invariant that we're using is the absolute cross ratio. So just to remind everyone, we're familiar with the cross ratio of 4 points in the extended complex plane having this formula here. And the absolute cross ratio, it looks similar. It's for 4 points in the 1-point compactification of Rn. It has a formula that looks really close to that, except that it's just Euclidean distance between the 2 points used instead. So the important takeaway here for absolute cross ratio is that it's an invariant of ordered 4 tuples under inversive transformations. So that's where it gains its utility here. So we're going to go and look in Lorentz space like Crane and Short do, because there's a lot of easy setup that can happen here. There's some really cool correspondences. So just to set up Lorentz space, I have a picture over here of n+1 space. And of course, I can only draw 3 dimensions at most here. So our picture is gonna have to represent R3, and this being R2 in that case. And so Lorentz space is just n+1 space equipped with the Lorentz inner product given by this formula here. And so for convenience, what I've drawn as well is the light cone, this double cone, which we can use to understand this sort of type that goes with vectors and subspaces. They come in 3 flavors. They come in space-like, time-like, and light-like as subspaces. And so using this light cone as a reference, we can sort of think of this space out here as the outside of the light cone, You can be on the light cone or you can be inside the light cone. And if you are a subspace that only intersects the light cone at the origin, you're a space-like subspace. If you're a time-like subspace if you contain a time-like vector, and a time-like vector is a vector that's inside the light cone. And then you're light-like otherwise, and that is gonna just be when you are a subspace that intersects the light cone in a line, and a light-like line. So a light-like line is just a ray on the light cone. So additionally, the light cone here can help us pick out some important key features. At level 1, the light cone intersects to give us the n-1 sphere, and that n-1 sphere is serving as the ideal boundary of the Klein model of hyperbolic n space. And so this is where all of the objects that we're interested in are lying. The circles on the the spheres and the points on the n-1 sphere are happening on this n-1 sphere here. And so we have those geometries within Lorentz space here. And moreover, the movements, the Lorentz transformations are linear transformations that preserve the Lorentz inner product. And we're interested in those because they are key to understanding what's happening in the other spaces. We have that the positive Lorentz transformations, which are given by the positive orthogonal group here, are isomorphic to the isometries of hyperbolic n space, and those are in turn isomorphic to our inversive transformations of the n-1 sphere. And so positive Lorentz transformations are just Lorentz transformations that are taking positive time-like vectors to positive time-like vectors. Positive just meaning that their n+1 coordinate is positive. If we're interested in orientation preserving, then we have this relationship down below too. So if we're looking at an n-2 sphere in the n-1 sphere, in our picture that looks like just these 2 points, because this is S1, so our n-2 sphere is represented by those 2 points there. Then within hyperbolic n space, that's going to pick out a hyperplane to go with it. And that in turn is going to correspond to a time-like subspace that intersects that hyperbolic n space as that hyperplane. And we complete this by getting to space-like unit vectors. There's one space-like unit vector, one positive space-like unit vector that gets picked out from an n-2 sphere in the n-1 sphere because it's Lorentz orthogonal to this time-like subspace here. So we have a nice correspondence between every time we have an n-2 sphere in the n-1 sphere that can be represented by a space-like vector, a positive space-like unit vector. And moreover, we're looking at inversive distance. We have this nice equality that the inversive distance is equal to the negative of the Lorentz inner product. So that's our correspondence for spheres in the n-1 sphere. For points in the n-1 sphere, that's going to, if we're thinking in hyperbolic n space, those are going to be our ideal points of hyperbolic n space. And then that's going to in turn correspond to light-like lines in a light-like line in n+1 space. And I'm being careful here to say a line rather than picking out a particular vector, because there is no like natural choice for a light-like vector to be chosen there, because there's no concept of a unit vector for light-like vectors. Light-like vectors have a norm of 0, so always. So they we don't have this concept of a unit vector for light-like vectors. So instead, we just say we use the whole light-like line to represent a point in the n-1 sphere. So when we're looking at the absolute cross ratio of 4 points on the n-1 sphere, there's a relationship between that if you square it to a formula involving the Lorentz inner product of 4 chosen vectors to represent those points. And so in this case, it's okay to choose vectors to represent those points in the n-1 sphere, because this formula involves using that choice of vector both in the numerator and the denominator. So your choice of vector there is not going to affect this number, because any magnitude is canceled out from the top and on the bottom there. So it's this formula is independent of your choice of vector for each of A, B, C, and D. The last part I want to bring up is points in the hyperbolic space, because they have a nice correspondence too. They're picked out by positive time-like unit vectors in n+1 space. For every one of those points, there's a positive time-like unit vector going through it that we can pick. And then the nice relationship there is that the Lorentz inner product of 2 of those such vectors is equal to the hyperbolic cosine of the hyperbolic distance between those 2 points there. So in this way, we can sort of translate anything that we might be interested in hyperbolic n space or spheres in the n-1 sphere, points in the n-1 sphere, into language in Lorentz space. The difficulty comes in, though, when you start asking about comparing points in the n-1 sphere to spheres in the n-1 sphere, because if we look at, as we said before, if we choose a vector to represent a point in the n-1 sphere, then that choice, if we just look at the Lorentz inner product between that and a space-like unit vector, is not going to tell me much, because there's no well-defined choice to make for that point in the n-1 sphere. So as you go farther out on this line, you're changing the Lorentz inner product that's happening there. And so the workaround for this is to look at the Lorentz inner product for a chosen vector on that light-like line, and 2 space-like unit vectors instead. And this is where the notion of the Lorentz ratio comes in. This is, you take 2 fixed unit vectors, and they at this point really don't have to be anything. They can be like space-like, light-like, or I should say space-like or time-like. But we'll see in a bit that gets, we'll specify a little bit more after this. But for the purposes of this definition, oh no, sorry, that is a little bit of a mistake. That I should say that W1 and W2 have to be both space-like or both time-like for the purposes of my definition. So either both space-like unit vectors or both time-like unit vectors. And then the Lorentz ratio that is the following. You take a vector, any vector you want in that light-like line, and you plug it into the formula like this, and that's going to give you the Lorentz ratio for that point, or sorry, that light-like vector with those 2 either space-like unit vectors or time-like unit vectors. And this is a way to compare information involving a point on the n-1 sphere to either 2 spheres on the n-1 sphere, or if we're thinking in hyperbolic n space, we can think compare 2 points in hyperbolic space to a point in the ideal boundary. So we'll look at that correspondence in those geometries in a bit. But what I want to emphasize here is that, of course, you can look at the Lorentz inner product of any light-like vector with any space-like vector or any time-like vector. But the goal here is to find something that transfers into geometric information in other geometries. So that's why this definition's been created. Because when we go and when we have that now, we can create a rigidity statement for involving space-like and time-like vectors and light-like lines that says the following, that I just need my 2 collections to have a basis of either all space-like unit vectors or all time-like unit vectors. And I need to know that that basis of vectors is has correspondingly equal Lorentz inner products. And if I know then for all the vectors outside of that basis, if I know the Lorentz inner product to from every vector outside of that basis to every vector inside of the basis is correspondingly equal. And if I know that the Lorentz ratio of every line outside of the basis to every 2 vectors inside of the basis is correspondingly equal, then I know that there's a Lorentz transformation taking one collection to the other. And so again, this isn't, it's not very interesting. It's not a very interesting modification from anything that Crane and Short have done as far as the Lorentz case goes. It's when we get to looking at the hyperbolic geometry and the geometry of circles and or spheres in the n-1 sphere where this becomes more interesting. One thing I do want to note here is that by what I'm trading out from what Crane and Shorter have done is instead of requiring all inversive distances or all information be known, I'm able to say that we're only looking at a basis. We only need to know the Lorentz inner product between vectors outside of the basis to vectors inside of the basis, and only the Lorentz ratio of lines outside of the basis to pairs inside of the basis. This is a reduction of information, but it's a trade-off of information too, because they don't have as much restrictions on what's going on with their requirements for all they required for their conditions was that all of their circles, for instance, or all of their spheres, for instance, not have a point in common. But we're going to see that my requirements are a little bit more strict as far as qualitative information goes. So it's sort of a trade-off for from qualitative information to quantitative information. But beyond that, all I've said so far is that there's a Lorentz transformation taking one collection to the other. What makes it positive? So that Lorentz transformation is either positive or negative. And from there, then if it's positive, you're good. But if it's not, then the modification to the statement is that what you can say is that the negative of the Lorentz transformation you found is positive. And so it's going to take the negative versions of all these vectors to the vectors over here. Okay, so that vector space, the Lorentz space version of that statement can be translated into a statement for hyperbolic n space. So just to introduce my view that I have here now, we're looking in the upper half space model of hyperbolic n space. So this is a three-dimensional picture of hyperbolic end space here, which means that my extrinsic view of Lorentz space is going to look four-dimensional, which means that if I'm looking at a basis for R4, then of course I have four vectors. So at this point, we want to sort of characterize what's happening with the hyperplanes that are corresponding to if I have four space-like vectors being my basis, for instance. So in that case, what does that basis of space-like unit vectors do to the collection of four hyperplanes involved? And so we're going to characterize it by what it can't be. And first of all, they aren't all orthogonal to a common hyperplane. So we can't have that, that each of these hyperplanes, if we look at the ideal boundary circles, that they're orthogonal there. We can't have that they share a common point in the ideal boundary. And we can't have that they're isometric to a collection of hyperplanes containing this point here. So each of those conditions is just corresponding to what would happen if you didn't have a basis, if you had that they were actually if all of your four vectors that you're looking at were actually in a subspace that's a lower dimension. So if we're looking at a basis of time-like unit vectors, then all that looks like for us is that it corresponds to a collection of, in our picture here, four hyperbolic points that are independent, meaning they don't all lie on the same common hyperplane. So for instance, in this picture, we can see that these three here lie on this hyperplane, but the fourth is not. And the same is true for all the faces that we're looking at. So with this, then, we're able to talk about, with this correspondence, a collection of intermingled points and hyperplanes in hyperbolic end space. So in my picture here, then I have some hyperplanes, and I have points in hyperbolic space, and I also have these ideal points here as well. And so I'm either going to take a basis of four hyperbolic points, or I'm going to take a basis of four hyperplanes. And you know, I have two collections that look like this. And I, again, need to have that certain information is correspondingly equal between my, my two bases. So to talk about what the conformal invariants look like here, between hyperplanes, you're going to be measuring hyperbolic distance if they are disjoint and hyperbolic angle if they're intersecting. If you're looking at comparing hyperbolic points with points or hyperbolic points with planes, then you're looking at the hyperbolic distance between them. And if you are looking at ideal points, then you're going to be comparing those ideal points to your objects in your basis through what I'm calling the hyperbolic ratio. And to give an idea of what that looks like for us, the hyperbolic ratio can be if you have an ideal point and two fixed hyperplanes, then take a sequence of hyperplanes, for instance. So if you're comparing it to hyperplanes like this, you would take a sequence of hyperplanes limiting to that point, and you would look at the limit of this ratio, the hyperbolic cosine of that hyperbolic distance for each of those hyperplanes there. Because this is limiting to a point, that means that that hyperbolic distance is going off to zero, going off to infinity between each of these hyperplanes. And so we're looking at, because they're going off to infinity at the same rate, it comes out to a number. So the number, the interesting thing here is that the hyperbolic ratio is the Lorentz ratio, which in turn is what I'm also calling the inversive ratio when you get to looking at spheres on the n-1 sphere. So just to go back to Lorentz space real quick, so that sequence of hyperplanes, for instance, corresponds to looking at a sequence of space-like unit vectors that's limiting to this light-like line. And so it's just a pretty simple continuity argument to say that that limit of that ratio is going to limit to that Lorentz ratio that we saw earlier. And of course, you could also be doing this for hyperbolic points as well. You can, if you are looking at the hyperbolic ratio, but using two fixed hyperbolic points instead, because your basis is made of hyperbolic points, then you would be taking a hyperbolic, or sorry, a limit of hyperbolic points to that light-like line. So from here, it's a pretty clear-cut direction towards looking at spheres and points on the n-1 sphere from that hyperbolic space statement. The only thing I haven't really mentioned much of at this point is that what to do with the interior balls that go with these spheres. I've sort of been sweeping that information under the rug. And just to talk about it a little bit briefly here, for every sphere that we have, we do have a choice of which interior ball to pick. And so how do we choose the correct space-like unit vector to go with it then? And it's there's a nice way to do it. You can do the following. So you have, if you have a sphere in the n-1 sphere, you can take the cone point by taking all of the lines that are tangent to the sphere, the n-1 sphere, through a point on the sphere you're looking at, and they'll cone. They'll all reach a cone point outside in n space, and so with that, then, if you consider the time-like subspace that is intersecting the n-1 sphere to create this sphere here, and if you're picking out an interior ball, then you're picking out a half space to go with that time-like subspace. If that half space that you picked out contains that cone point, then you can represent that with the positive version of the space-like unit vector corresponding to that sphere. And if your half space that you've chosen doesn't contain that cone point, you would represent it with the negative version, the negative space-like unit vector. Okay, so in that way, the choice of interior ball can be represented with your choice of whether you're looking at positive space-like unit vector or negative space-like unit vector. And at this point, I just wanted to say, a little bit about why I'm interested in switching out, being okay with this trade-off of looking at a restricted view of what I'll allow for the objects, sort of the conditions on my spheres in the n-1 sphere, or I guess I'll just say circles at this point, because this is the motivation for it. So with my rigidity statement, says that what I have to have in my collection is a basis for the n+1 space that I'm looking at. So if I'm looking at circles in the 2 sphere, then that means I have to have a collection of 4 circles that correspond to a basis of vectors for R4. And so that means here that there's a restriction on what I am allowed, or what I must see happen in my collection of circles. Specifically, I have to have 4 circles that we call independent, which means do not belong to the same circle plane. And so to just categorize what a circle plane is, there's a hyperbolic circle plane, or C-plane, is a C-plane where all circles are orthogonal to a common circle here. Like in this picture, these four purple circles are orthogonal to this pink circle. They can't all be containing the same point, so that's what's called a parabolic C-plane. And they can't be Mobius equivalent to a collection of great circles. And so Crane and Short's condition that the collections of circles can't all contain a common point is gotten from this parabolic C-plane here. So my collections with the independent subcollection, I can't have the circles contain a common point, but I also can't have these other two restrictions as well. To me, this is a nice trade-off because of where I am interested in using this. So I'm interested in using this in, I'll just say a little bit at the end, circle polyhedra. And so circle polyhedra, have polygonal faces. And so this idea of circles being independent is sort of an okay thing to ask. But so there's a restriction on what I'm allowing here. I am not allowing hyperbolic C-plane or elliptic C-plane for the independent, for the collection of, for a collection of four circles. I need a collection of four circles that are independent here. So just to have it on the screen here, here's my theorem. It looks sort of similar. I just wrote it in the version for circles here, though. It states that if you have two collections of oriented circles and points in the two-sphere, and you suppose that each has an independent subcollection of four circles, where these these points that you have are not in the circles in your independent subcollection, then there's a unique inversive transformation such that either that inversive transformation takes all of the circles in one collection to the other and all the points in one collection to the other, or it switches the interior balls of one collection and takes it to the other, and takes all the points in one collection to the other. And that happens if and only if you have the inversive distance between each of your circles outside the subcollection to each of your circles inside the collection, inside the independent collection, is correspondingly equal across both collections of circles. And that each of your Lorentz, each of your inversive ratios is correspondingly equal as well. Okay, so at this point, I wanted to say that, even though it's easy to find an independent subcollection of four circles in any given collection, it's not really reasonable to expect that that's what information people are working with. It's not really reasonable to expect that the collection of information that everyone's working with is where the inversive distance from everything in your collection to an independent subcollection. It's much more typical for people to work with things in triangulation patterns, of course, or something more spread out. And so one of the questions is like, how could we start like maybe using this statement as posed in other contexts? And so one thing I want to look at is inversive distance circle packings. So here's an octahedral graph, and inversive distance circle packings are where your vertices are representing circles, but when you have an edge between it, it means you know the inversive distance between them. And so now this can allow for intersections of those two circles, those circles could be disjoint or they could be tangent. It could be any one of those things happening. And in particular, one thing that's interesting is that Bowers and Bowers in their paper Mosh, Linker, C octahedron, the two-sphere, constructed a counterexample for showing that these things aren't always rigid as is. For example, with what we have here, if we take these 3 yellow circles with the 3 pink circles and consider that to be one collection, where we know the inversive distances in this pattern, and we have another collection composed of those 3 yellow circles with the 3 purple circles now, those 2 collections have the same inversive distance information known in this pattern, but there's no Mobius transformation taking one collection to the other. In particular, the problem is that these 3 circles are remaining fixed while these outer circles are moving. And so the only inversive distance the only Mobius transformation fixing those 3 circles would be the identity, but the identity is not going to take one collection to the other. So one thing that what we're looking at could be useful for is could be done in the following way. How can we make this thing rigid? The proposed idea is to take a dual graph where you have every one of the faces is represented by a vertex now, and you this is a this is a subgraph. Sorry, it's a subgraph of the dual graph, where you make a spanning tree about all the faces. So so this is just one example of what you could do, and then play a game where you add in one edge here, and this edge represents now knowing the inversive distance between the circle represented here and the circle represented here. And so now what you have is you know the inversive distances completely between these 4 circles. And then if you know that, then you know that there's a Mobius transformation taking those 4 in the collection to the other 4 in the collection. And then you keep going, you play the same game separately with the 4 circles here, where you add in this edge. And so now that represents knowing all 4 inversive distances between these 4 circles. All the inversive distances between these 4 circles, which means that there's a Mobius transformation between taking these 4 circles to the other 4 in the collection. But if you have 2 Mobius transformations, one taking or both taking the same 3 circles to the same 3 circles, then they must be the same Mobius transformation. You continue on in this way until you have completed it for all the circles in both configurations, and that would give you a Mobius transformation taking one collection to the other. And the interesting thing is that those pieces I deleted were never used, but also neither were these outer pieces here. And so maybe this independence notion could be used in this way to be an algorithm that we can use to rigidify things that aren't rigid. Of course, the problem here now is that this isn't circle packing anymore, but we now know it's rigid. So I guess the question is whether or not that would be helpful to sort of turn qualitative conditions into quantitative conditions qualitative information into quantitative information. Like if there's something that we could relate knowing this extra information to, then like for instance, convexity, that's something like having a notion of convexity for circle packings, which Bowers and Bowers Pratt do in one of their papers, then yeah, I think that might be useful for something like that. The other thing I'm really interested in is exploring is taking that inversive ratio and seeing whether it has a use in other areas. If it has a use for projective, for rigidity of projective polyhedra and rigidity of circle polyhedra, I'd be interested in seeing whether or not it could be used there as well. I'm interested in seeing whether it has a use beyond the context that I've used it in. So there's my references. Thanks.
So thank you very much. Why don't I open the floor up for questions, and you can just unmute yourself and jump in.
So in terms of the original rigidity question for inversive distance circle packings.
Yeah.
So you have certain, with that one pattern with 6 circles, you have certain inversive distances where it's not unique. And so I'm curious, you made a statement as you looked at the tree and the dual, the spanning tree, and started adding edges, that you can get inversive distance prescriptions, but not circles. So can you figure out with circles remaining involved whether you can specify, rigidify, and get a circle packing of the rigid result, or is that difficulty?
So okay, so sorry, I'm not understanding the question, I don't think. You're saying, can I, whether or not I can take what I've made with the adding in the extra edges, whether I can turn that into a circle packing? Is that the question?
Yeah, and in other words, if I have a flexible pattern, can you figure out how to rigidify it by adding, you added 3 pieces of information, right? And so that each piece is a flex, and you're fixing one of the possible modes of non-uniqueness.
Yeah.
Right.
Yeah.
And so can you do that by adjusting the circles and saying, now that I've fixed this additional inversive distance, now I have to adjust some of the other circles, but I get a circle packing at the end with the new information and the original.
I mean, I haven't figured out how to do it yet, but I want to work on it. I want to keep working on it. So like I said, I have actually like a rigidity statement for like when you add in extra pieces of information, but I don't know how to transfer it yet to like the pieces that, like, for instance, weren't used. I worked on it like a lot towards the end of my dissertation, and I couldn't come up with anything yet on how to do that, but it's something that I want to look at again.
Well, maybe Phil, maybe you or John have an idea on that.
But this thing also looks like the graph that you're looking at is the octahedron, right?
Yeah, yeah.
And this is the same as the what is it? The flexible Snelson model, right? It has if you take the Snelson tensegrity and you don't put it in its usual position, it has 2 configurations. And that's sort of what's going on here, isn't it?
Okay.
So what John seems to be saying is that can you do it with, instead of just having inversive distances, have them as circles in contact or something like that, so that the ones that are in contact are, so that these edge lengths are actually circles in contact. Is that fair? So
Not
some
sure
of the
what my
circles,
question is, but I throw it out and hope that someone out there smarter than me picks up on if there's any idea in it.
yeah, but the circles can overlap, like in this lower picture. So that's okay.
Yeah.
The circles that aren't, but as part of the graph, can overlap, right?
Yeah.
And then you have some fixed inversive distances between some pairs of the circles.
Right.
So can you arrange it so that that inversive distance is whatever the 1 - 1, whatever it is when they're in external contact? I kind of remember talking to them about this. That
Okay.
that's possible.
You said, is it Snelson? Is that?
Snelson, yes. Oh, I have models here.
She do.
There you go.
Snelson's tensegrity is Schoenhardt's twisted octahedron.
Oh, okay. Right. Yeah.
No, I don't have it here. I have it in my at home, but it's two triangles twisted,
Right.
one above the other, twisted. That's all. And then it's the same pattern of an octahedron. So it's an infinitesimally, if you take an infinitesimally flexible octahedron, that's what the Snelson is.
Yeah.
Then you can do a push me pull you, and you get two tetrahedra that flop from one to the other.
And this is what Ma and Schlenker did to generate
Yeah.
their examples using Pogorelov maps. So they started with the
That's
Schoenhardt
right. That's
octahedron.
right. That's right.
Are there examples known with more than two configurations that satisfy given?
I'm still listening to talks.
It's almost.
You mean, can you elaborate on that? Do you mean flexible or finite?
I mean, more than two, yeah. So
More than any more than two?
So sorry, I think I missed the question. What was the question?
So are there examples of inversive distance specifications on triangulations of the sphere for which there are finitely many, but more than two
Oh,
solutions?
yeah, I don't know off the top of my head.
I would
any other
imagine.
examples.
Maybe you can just glue some of these together to do that,
Yeah.
but that's kind of cheating.
Who's against cheating?
And then, John, the other question that you thought I might be asking, the actual flexibility, I guess the answer is no.
I can show you constructions where the answer is yes.
Oh, really? The question I was actually going to ask is, if you fix a triangulation and you fix an actual collection of circles, is there something like a matroid that describes the sets of inversive distances which suffice to rigidify that collection?
Oh gosh, I think you're asking the wrong person. I don't know a lot of rigidity theory stuff as is, and it's definitely something that I need to look further into.
This example, you could take all of the inversive distances corresponding to the edges of the octahedron, plus one more corresponding to a dual edge.
Right.
And any one extra would be enough.
Okay.
So there's a little bit like minimal circuits in a matroid or something like that.
There's a lot of things to look into further, though. That's for sure.
Could you say your theorem again?
Yeah, go back to the
Right.
this. Mhm.
Oh, here it is.
Right. So I guess you can also ask about whether you need all of the triples in the very last line.
Yeah, I guess. I mean, I assumed that. Yeah, I guess you're right that maybe things get repeated enough that. But I assumed that it wouldn't. you wouldn't need to, or you wouldn't be able to go any further reduce with this because those are from the basis. The CI and CJ are from the basis of circles. But
But maybe you only need 3 of them instead of 4.
yeah. No, that's a good question.
Yeah, it just seems like a lot of information that if you know all this, if you know all the CIs,
Right.
then that's giving you an error. Okay, so thinking about it in higher dimensions.
So this is really a global result. Is that right?
Yeah. Yes, it is. Yeah.
Right.
So if you were working in an arbitrary dimension, then your independent collections would have more elements in, because they
Yeah.
correspond to a basic, so they have n+1 elements.
Right.
And then in these triples, for each point, so for each light vector, you're going to be specifying n+1 choose 2 numbers.
Yeah.
Which seems like more than you need.
Okay.
To specify.
All right. Yeah. Yeah. Can I reduce that information? So reduce.
Yeah. So in your
Good question.
note here, it's 6. I guess it's 6 numbers when you should only need 3.
Yeah. Well, I guess that's a new a new extra thing to look into then.
Yeah. It was nice to be reminded of my old paper. I did.
I gotta say, I was excited to finally meet you.
Well, and anything to do with it being well written, that old paper was all down to Ian, not to me.
Yeah, no, it really holds up. There were a lot of things that a lot of the time I was like, is that true? That seems like, and then I would think about it for a really long time. I'm like, oh yeah, it's definitely true.
I always worked really closely.
Everything's very concisely written too.
Well, it's from the old days when journals were printed on paper. You had to make it short.
Yeah. Well, what is it now? How long should I be aiming for now for a paper? Is anything allowed?
More explanation is usually better.
Yeah.
Yeah.
Well, I was nervous to give this talk here, but I'm excited. I'm happy to share the information with you, Ed Crane.
Yeah, well, I'm happy to see what you've done. I didn't even consider that we were using way too much information.
Yeah, you did. You.
I mean, in the proof we used a basis, so.
Yeah, I mean, the more I thought about it, though, like I said, it's a trade-off of information. So it is a reduction, but with a price a little bit. But it's not a bad price, I don't think, to pay.
Right. In my own implementations of circle packing algorithms, I often use the vectors in Lorentz space.
Yeah.
And I think
it's
computer graphics do as well.
It's really not much of a trade-off, because if you don't have an independent set, then that just pushes the whole problem down a dimension. And that I know you haven't worked that out, but it's an easier problem.
Oh.
I mean, if all the circles lie on one of the C planes, then you need even less information.
Yeah.
You work in a subspace. You work in a subspace.
Right. Yeah. I have been thinking about that one a little bit, but some of the lemmas that actually that Ed has in his paper are sort of relevant to that, and I wanted to just make sure that I don't say anything wrong with when you do have a basis for a lower dimension, like what happens with it. But yeah.
I'm pretty sure we all say everything wrong when we give a talk.
It's been a while since I've given a research talk. It's been since since summer, and it's been a long 2 semesters here of just doing a bunch of teaching instead.
You've
A little harder than that pre-calculus, huh?
Yeah, takes up a lot of time.
What did you use to make those nice figures with the hyperboloids? And...
Actually, I used PowerPoint for a lot of them, but I use GeoGebra a lot more now for my images. So I think as I make more talks, it'll look even prettier. Yeah, the images, I actually just made by hand a lot of them in PowerPoint.